All right, now section 2.8, we have what's called cis and trans isomers. All right, cis and trans isomers only occur on restricted bond rotation molecules. I know it sounds a little weird, but it's basically molecules that have a restricted bond rotation. If you look at a cyclical compound, let's take cyclohexane for an example, okay, I cannot take this bond right here and rotate all of the groups all the way around. Okay, I can't rotate the bonds at all. These bonds do not rotate. All right, like how we saw with a straight chain molecule. All right, let's say I have a straight chain molecule. I can easily rotate around that bond. So this group right here can be rotated all the way around and all the way around the other way. I can rotate these bonds. Okay. Well, these cis and trans isomers only occur on these molecules where you cannot rotate the molecule. Because if you can rotate them, you don't have cis and trans. Okay. So it only occurs on molecules that do not have rotation. It occurs on cyclical compounds. We'll also see that this also occurs on alkenes, which will be, I believe, next chapter. Okay, so let's talk about what cis and trans implies. Okay, let's take a three-membered ring, a cyclopropane. I'm going to try to draw it three-dimensionally. Okay, and what you have is you have hydrogens that are kind of on the top of this molecule, and you have hydrogens on the bottom of the molecule. Okay, see these three hydrogens, like that's kind of drawn bad, but these three are on top. The hydrogen should be more down like that. And then you have these three hydrogens that are on the bottom face of the molecule. Notice that no matter, I can't rotate these carbon-carbon bonds so that these hydrogens are then on the bottom and these hydrogens rotate on top. If I turn the molecule around, that's one thing, but I can't rotate them. So because of that, if you have different groups, let's say you have methyl groups. So let's say we have this molecule where you have a CH, where both of your methyl groups are on the top face, and you got hydrogens coming down. All right, I'm not going to draw the hydrogens there, just to show you the difference between the cis and trans. So these hydrogens are on top. There's nothing I can do to this molecule to put one methyl group on the bottom. Okay, that is a different molecule. That would be a CH3 here with the hydrogen down there, hydrogen here, and the methyl group on the bottom. And our frame of reference is the plane of the molecule. Okay, I'm sorry, the plane of the carbons. Okay, so this would be the top face. These hydrogens would be on the bottom face. Okay, so these are what cis and trans isomers are. When the two methyls are on the same side, that's the cis isomer, for same side. And when the two methyl groups are on the opposite sides, that's called the trans. Okay, opposite. All right, so I'm kind of drawing a three-dimensional structure, but you can actually draw these in a two-dimensional with wedges and a dotted line. All right, so I can take a cyclohexane, and if I draw a wedge here, put a methyl group here, and then do another wedge at the 4 position, all right, these groups are on the same side. So this would be the cis isomer. You can also draw it where you have one of them is wedging out, meaning coming out towards you, and the other one, the other methyl group, is going back. Okay, now what I didn't draw in there is the imaginary hydrogen. Not imaginary. I didn't draw in the hydrogens. Okay, so technically on the molecule on the left, you would actually have a hydrogen going back and another hydrogen going back. So notice your hydrogens are on the same side of the molecule and your methyls are on the same side of the molecule. What I would do is make models if you can't see this. Okay, the models will be very easy. In class, in lab, our first lab, we'll do an actual model lab where we make the models of all these molecules and you'll be able to see it. So here your hydrogen is going back, but here your hydrogen is coming up. I'm just kind of doing it little so so that it doesn't encumber the molecule. So these are two technically different molecules. The molecule on the left would be called cis 1,4-dimethyl cyclohexane. And the molecule on the right would be called, I need more room here, so this molecule, that's the name of that molecule. This molecule is called trans 1,4-dimethylcyclohexane. All right, and these are isomers, but these are in particular called stereoisomers. So we learned about constitutional isomers, same formula, but the structures are completely different. Stereoisomers is same molecule, but they are different in 3 dimensions, let's call it in a 3D orientation. So they are connected to the same atoms. That's the important thing. The connection is the same. Connection is the same. What do I mean by connection? I mean that your methyl groups are still connected to the 1 and the 4, and you still have a cyclohexane. A constitutional isomer would be if you have like a 3-membered ring compared to the 6-membered ring. I mean, the molecule is just totally is a different molecule. There's nothing similar about it. But these molecules, I mean, are almost identical. It's just how in 3 dimensions they are not the same. So that's what a stereoisomer is, and we'll learn a lot more about stereoisomers later on in the semester. All right, just how we just talked about conformation of alkanes, straight chain alkanes, we're also going to talk about conformation of cyclo alkanes. So 2.9, it's going to start talking more about how cyclo alkanes actually exist. All right, I want to start with a few of the cyclo alkanes, particular cyclopropane. Cyclopropane is a very strained molecule. All right, it has what's called ring strain. Okay, so what is ring strain? Notice the bond angles here are 60 degrees. Okay, well these are sp3 hybridized carbons. sp3 hybridized carbons, if you remember, prefer 109.5. So we're about 50 degrees lower than what it wants. So because of that, these molecules are relatively high in energy because of this ring strain. Okay, so these bonds actually want to break. But you can form cyclopropanes, but they're just not stable. All right, for cyclobutane, your bond angles are 90 degrees. A lot better than 60, but still not quite at that 109.5 that it wants to be at. All right, so actually the ring actually does not sit flat. It actually has like a puckered shape to it. All right. It kind of looks, the best thing to do is to take your models and to kind of make these, and you'll see that that's actually how the ring exists. The backbone and the hydrogens are kind of in the corresponding place. But that's kind of what these molecules tend to do. 5-membered ring, same thing. It kind of adopts a different shape. It's definitely more stable than the 3 and the 4-membered ring, but it's not perfect. All right. So one, it does have a puckered shape to it, a puckered shape. However, you still have eclipsing interactions and Gaussian interactions and things like that. All right. However, 6-membered ring, when you get the cyclohexane, all right, for cyclohexane adopts what's called a chair conformation. All right, and this chair conformation alleviates all of that strain. Okay, so actually, cyclohexane exists like this. All right, the pictures in the book are a little better. You might want to practice drawing your chair conformations because you're going to have to be able to do it. But this is kind of what it adopts. It's a 6-membered ring, and it looks like a chair where here is the back part of it, and here's the bottom part of it. You can even flip the ring. It's what's called ring flip, in which this comes up and this carbon comes down. So it looks like this. Okay, and what you're going to find, which is very interesting about this, is that it alleviates all the ring strain. So this has no ring strain whatsoever. What happens is is every bond angle now is 109.5. Okay. The second thing it does is, which you can't tell, but if you look at the flat molecule, all right, let's look at it on the side. Let me actually turn the page here. Wait 1 second. Okay, if you look at the flat molecule, the flat 6-membered ring molecule. So, again, trying the best I can on my art skills. But your hydrogens kind of look like this. Okay. What you'll notice, again, it's hard to see on the picture, but if you draw your molecules, notice that all of the hydrogens are in the eclipsed conformation. Okay, and we said eclipsing bad, don't want eclipsing, we want everything to be staggered. All right, so if this adopts a ring conformation, what happens is not only are your bond angles now all at 109.5, but your hydrogens now are all eclipsing. Again, you might not be able to see it from here. The best thing to do is to make the model, but you can kind of see that this hydrogen is kind of in between these two hydrogens. It's eclipsing those hydrogens. Okay, so make the model. You'll be able to see it a lot easier. You definitely need models for this, especially for people that are not able to see this. All right, section 2.10, we're going to talk more about these hydrogens on this chair conformation. The remainder of the chapter is about these chair conformations. And the day that we do the lab on Newman projections, we also do a lab on these chair conformations. So we're going to get a lot more practice with this. This is just kind of to introduce you to it, and hopefully you can start playing around with your models. All right, so we're going to talk about what's called axial and equatorial bonds. So these chairs, so let me draw another chair conformation. All right, there are two types of hydrogens. There are the axial hydrogens. So these hydrogens go straight up. Hydrogen there, hydrogen there, hydrogen, hydrogen. Remember, there's two hydrogens on every carbon on this molecule. These are what's called the axial hydrogens. It's the hydrogens in the axis. All right, they're going straight up and down. Those are the axials. Now, if you take the chair conformation now and you look at the other hydrogens, these hydrogens are in what's called the equatorial because they're around the equator, hence the name equatorial. Okay, so there are two types of hydrogens, axial, equatorial. Let me draw it again. We'll draw it bigger, and we'll draw it with all of the axials. So here are the axial hydrogens. What I like to do, you'll see in class, is when I make the model, I like to make the axial hydrogens one color, and I like to make the equatorial hydrogens a different color so you can actually see them. All right, so that is cyclohexane in its full glory. You have the axials. Notice you have 3 on top, and you have 3 on the bottom. And then your equatorial ones are all the ones on the sides. You got one there. You should have 6 total. All right, what you might want to do is practice drawing these structures, especially practice drawing the chair conformations as well.